All right, it's time to start exploring some new stuff. This week we're going to talk about pulse width modulation. It's a difficult sounding concept, but it's actually fairly simple. Pulse width modulation is the act of taking a pulsed DC signal and adjusting the width of that pulse to accomplish any number of different things. In the example today, we'll be talking about controlling the brightness of LEDs, although pulse width modulation is also used in data signals. But we won't get into that maybe ever. But if we do, it'll be way far down the line. Anyway, so let's take a look at what a pulse width modulation signal will look like. So let's say we have a 50% duty cycle signal. That's going to look like this. Assuming this is your zero axis, we're going to have it on half of the time and off half of the time. So the duty cycle is just how long is it on in relation to how long it's off. So let's say we're looking, I don't need the y-axis, I don't know why I'm drawing that. Let's say 90%. Oh, my dry erase is doing that thing where it leaks. There we go. So a 90% pulse width modulated signal is going to be on 90% of the time and off 10% of the time. And then, of course, on the other end of the spectrum, we could have a 10%, and that'll look, oh, no, it's still doing it. Why are you doing that? So go back in there. Huh. I wonder what's going on with my markers here. Anyway, a 10% modulated signal is going to look like this. Sort of. Now, the circuit that I will be demonstrating for you today, I got a little ahead of myself in erasing there, but let's go ahead and make that go away. We're going to be using good old standard triple nickel timer, or 555 timer. Now, the circuit for a pulse width modulation using a 555 timer, I'm going to use a block diagram here, looks a little bit like this. We're going to have plus voltage, and pins 4 and 8 are here. They just go to the positive voltage. I'm going to just erase this here. 7, 6, and 2. Just got to reference my off-screen circuit diagram here. Pin 1 and 5, and pin 3. Pin 3 is out. So that's the signal that comes out of the triple nickel timer. Then 5 is just left floating, or if you want, you can also tie it to ground. That's the reset pin. And then we're going to have our 0 volts, or, well, actually we'll say minus down here. Pin 1 is just going to tie directly to ground. Pin 2 and 6 are going to be tied to each other, but pin 2 is going to come out, and you'll have a capacitor. Actually, I have this wrong on pin 1. Pin 1 is better with a really low value, like 1 nanofarad capacitor on it, just to completely decouple it. Then, this is a very complicated circuit, bear with me. R2, R1, R1, and then across R2 we have some sort of diode. If you're doing high-speed pulse width modulation, you need a fast recovery diode. Oh, let's see, am I missing anything? Nope. So that's what a pulse width modulator looks like with a 555 timer. Now, how do we decide what components we want? Well, the frequency is equal to 1.44 over R1 plus R2 times C. So typically what you'll do is you'll start with some known values of resistors. For 50% pulse width modulation, those resistors will be equal values. And then you either solve for F or you solve for C. Personally, I have an app that does the calculations for me because this is long, complicated math. Now, your high time is going to be equal to 0.69 times R1 times C. Your low time is going to be equal to 0.69 times resistor 2 times C. And last but not least, your duty cycle, the percentage of on time, is going to be equal to resistor 1 over resistor 1 plus resistor 2. So the duty cycle is directly proportional to R1 and R2. Now, for my demonstration here, I'm actually going to be having a potentiometer. Let's see if I can quickly draw in that potentiometer, if I have enough space here. Oh, I forgot to actually attach pin 7 anyway, so we'll rework this diagram real quick here. So we're going to have a resistor R1, and that's actually going to come out into a potentiometer, and then that'll come out to another resistor R2, and then the center tap of that potentiometer will come out to pin 7. You can also eliminate the potentiometer, but we want to adjust the duty cycle, and that's what we're doing with this potentiometer. The way you figure out the math for this one is half of the potentiometer plus this resistor is R1, and half of the potentiometer plus R2, this resistor is R2. The reason why you have these resistors on either side of the potentiometer is so that you don't crash the 555. Because if any of these values goes to 0, it doesn't know what to do, and it gets stuck. So you need some sort of minimum value on either side, which you can basically pick arbitrary values. I have a 2K resistor and 330 ohm resistors on either side, and I changed the value of C to accommodate the frequencies that I wanted to see. So that's the easiest way to do it. Just pick arbitrary values for the resistors and then calculate C. So this is all of this on paper. Why don't we have a look at it in practice? So bear with me a moment. There'll be a jump cut as I switch over to the experiment. All right, and now we're back with our pulse width modulation circuit setup. Now, what did I do with my pot trimmer? There it is. Okay, so let's have a look at just a slow flash. There we go, and the oscilloscope should be catching up shortly here. There we go. So here are pulses on the oscilloscope. Sorry for the strobing. I actually see that too, so that's just the refresh rate of the display is kind of slow. Let's actually decrease our time base here. No, that's the wrong way. I want to go this way, I think. Is that the right way? Yeah. So right now we're at 50% pulse width modulation. We can actually look at the duty cycle here is, well, 46.6. It's close enough. So let's adjust that duty cycle by tweaking this potentiometer, assuming I can get the trimmer tool to, there we go. So let's increase the duty cycle. This is a multi-turn potentiometer, so the change will be very gradual. But you'll notice it seems to be flashing faster, but it's actually not. It's flashing at the exact same rate. It's just staying on for longer. So you can see the time that it's on here on the graph is increasing, and the time that it's off is getting very short. And at some point, there we go, we're at maximum pulse width modulation, which according to the components I've set up is 99% duty cycle. So let's go off in the other direction now. I want to cover up the LEDs so you guys can see what's going on. I probably should have done some sort of flashing light warning for this, but maybe next time. Anyway, so let's go in the opposite direction. Let's reduce our duty cycle. Probably should have used a coarser potentiometer for this, but whatever. Anyway, so now as we're going further down, you can see the pulse width modulation. Now it's spending a lot of time off as opposed to on, and you can visually see that here. So why is this important? Well, in the case of controlling the brightness of LEDs, I'm going to bring this back up to about 50% again. Give me a moment. Just a little, oops, that's too far. In the case of flashing LEDs, no, I was going the right way, never mind. Don't be a dummy there, Chris. Why isn't this cooperating with me? Oh, the display is just refreshing really slowly. Okay, that makes sense. Bear with me just a moment. I want to set this to 50% for the next part of the experiment here. Oh, there's a big stereo just drove past. Okay, there we go. We're, well, close enough. Anyway, so pulse width modulation with LEDs, especially for lighting, is a difficult concept. Well, it's not a difficult concept, it's difficult to implement well. That's why I use a linear driver for these LEDs, because we don't run into problems. So what kind of problems do we see with pulse width modulation? Well, let's pull out this capacitor, and let's go for a higher value capacitor. We're going to increase the frequency of the flashing. All right, let's turn that back on. Now, you'll notice on the screen that there's oops, come on, go away. There we go. Let's change our time base here, switch to AC coupling. We'll actually get a bit of a better view of the graph there. Ignore the transient sort of angles on that. That's just because I'm using AC coupling to view a DC signal. So it doesn't display quite properly, but it at least triggers, so it holds the display steady. Anyway, so looking at this LED, I can't see anything going on. What frequency are we running at? We're running at 54 hertz. But I'm filming, that's 54 times a second. I'm filming at 60 frames a second. So the frequency of the flashing of the LED and the frequency of the shutter are not compatible. So you get this shimmer. And it gets worse if you dim the light. So let's decrease our duty cycle here. And you'll notice that shimmer is getting extremely noticeable. All right, that's as far down as it goes. I still can't see the flashing myself, but when I look at the screen of the camera, I can very clearly see the shimmer. And in fact, if I were to take it and wiggle it, it would probably be even more pronounced. Now if we take that duty cycle and increase it, let's bring it up into the 90% range. There we go. You'll notice the shimmer isn't as pronounced, but if I wiggle it, we'll still get a little bit of shimmer. But that's why pulse width modulating LEDs in a filming situation can be a little challenging. So let's bring this back to about 50% again. There we go. Let's go smaller. So let's pull out that capacitor. If anybody's following along at home, I started with a, what was this, 220 microfarad, then I moved down to a 10 micro. Let's move down to 0.22 micro. Now we're going to get up into the kilohertz. So let's turn that back on. Change our time base again to something more compatible with filming. Oh, that's actually a beautiful signal. Let's, oops, wrong way. Center this waveform up a little bit. That's good enough. All right, now let's start playing with the duty cycle of this. What are we running at? Let's see our frequency. Our frequency currently is 1.6 kilohertz. So we can now, let's reduce the brightness of the LED by reducing the duty cycle. Bring it all the way down to the minimum. And now there's no shimmer, but you can still very clearly see the brightness of the LED change. Now let's bring it up. And this is a very linear way of changing the brightness of LEDs. When you're using a linear driver, the brightness change on the LEDs is actually exponential. But when you're using pulse width modulation, the brightness of the LED changes in a linear fashion. So that, there's absolutely no shimmer at all. And at some point, I'm actually going to be setting up a pulse width modulation circuit to drive these LEDs through my linear driver. But that'll be an upgrade for later on down the road. Now I can make this even faster, but I don't think we'll be able to capture a decent waveform, because when I'm using this to drive my LEDs, I'm going to be running it at megahertz range. Yeah, I can't even get a solid waveform on that because I think this is only rated up to 200 kHz. And this is running at 1.2 megahertz. So the oscilloscope isn't going to give us a decent waveform. So anyway, that's a little primer on pulse width modulation. We'll probably do some more advanced topics in the future. If you haven't already, consider clicking here to subscribe. Right over here will be the... I just screwed up my outro, but let's keep it. Right here is going to be the subscribe button. Over here is going to be a video that YouTube thinks you'll like. Alright, let's try that again with a fresh battery. Right here is going to be the subscribe link. Over here is going to be a video that YouTube thinks you'll find interesting. Right here will be the Back to Basics playlist. And right here will be the Patreon link. Thanks so much, and we'll see you next time.